Welcome to the 17th lecture in the course Optimization and Data Science. The topic of this lecture is Principal Component Analysis. This is a topic we already touched when we were talking about regression, because we already had the singular value decomposition that was used to solve least squares problems there, so a regression problem. And we there also already had an example where how the singular value decomposition can be used for data compression and reduction. So this is somehow related. I come back to this topic now. So singular value decomposition basically is a method, and principal component analysis is one term that is used more for the analysis part that is using the singular value decomposition. And it has an interpretation also from the stochastic or statistic analysis part when we're regarding the data that we have as a covariance matrix. So the matrix that we apply our analysis on, if we consider it as being outcome or realizations of random variables. But this is more or less just another interpretation. So the principal component analysis, I treat this topic because it's a topic that is important in data science, data analysis. Basically, this is the identification of main components of a data set. If we combine the data set to a matrix, which is built out of different data vectors. So the main components or the principal components of the data are found and are analyzed. And the data vectors can be coming from different experiments or from observations of a system at different times. This is also an option. There are other names, so proper orthogonal decomposition is a term that's also used. This is more or less used for if the principal components are used for simulation, then for constructing reduced order models. And of course also singular value decomposition, SVD, is used, and there are also more names that can be used for the same method basically. We're studying this because it's one important method for data science and data analysis, and we can use the singular value decomposition or also an eigenvalue decomposition. And I will describe in this lecture the relation between the two things. We can analyze main components of the data. We can have a statistical interpretation, and we can reduce the complexity. This is one thing that we already had, and we can also analyze uncertainty in the data. And the basic idea is that we consider, if we go back to the stochastic interpretation, that we consider sample data vectors where each sample is already a vector. So we have here in the example m sample vectors, and each of these vectors is already n-dimensional. So we have a matrix basically. So if we take the data, the realizations of this random variable, then we have a data matrix, and it might be that this is consisting of m different measurements at n different spatial points. So this is a typical application, and the different measurements might be just different runs which we consider as being random, or we can also say these are snapshots, temporal snapshots. And this is my example in the picture. This is just a simple 1D simulation of a predator-prey model, so a model of an ecosystem in a spatial moving fluid. So it could be in the ocean, but it's only 1D. So we have n different spatial points, and we have here m temporal snapshots starting from here, and there's just a development in time. And so we can see this as temporal snapshots, but we can also just consider this as 8 data sets, which themselves, each of the data sets is a vector. So we can combine them somehow to a matrix. And yeah, we can of course apply all the techniques that we had, the estimators for the mean and for the variance, but now we can apply them in the first place to every component, which in my example would mean to every spatial coordinate, so a spatial index here going from 1 to 100. So, and this would be the j, so I can look at the mean of the 8 data sets that I have, compute the mean, and the mean I compute for every component separately. And then I get, of course, I can combine these means over the 8 data sets again to a vector, and I get here this orange line, which gives the mean value component-wise or element-wise of these spatial points. So this is just an application of the things that we had before. The mean, this is an unbiased estimator for the expectation of. So we can do the same thing for the variance. So here we have the unbiased estimator for component-wise variance. So again, we fix the j, so the spatial component. Then we compute here what we had in the last lecture as an unbiased estimator for the variance, taking here the difference to the mean and then squaring it and then dividing by m minus 1 here if we have m samples. So m here is 8. And I can also plot this so I get a spatial value for this variance, and I plotted this also, and to make it a little bit more clearly visible, I used here the square root of the variance, which is called the standard deviation. So I have again the data points, I have the mean, the orange one is the mean, and then I added and subtracted the standard deviation component wise. So the standard deviation is the square root of this term, and then I see the green and the red lines. And you can see that some of these data points are very clearly inside this range and some are outside. So this is something that I can do if I have this kind of data matrix. I can apply component-wise these operations, and here is again the how I put this data into a matrix. I can do it as I like. Here I did it in the way that I put the samples row-wise in a matrix. So the second index here indicates the spatial point, and so I have here one sample, one element of the sample, here another one, and so on and so on. And of course I can also compute the difference of this matrix now to the mean, or between the matrix, the data matrix and the mean, and I get this matrix here. So this is one way, and if we're considering the calculations, and if you look in the book, you have to always take care how the samples are put in the matrix, so the order, if it's row-wise or column-wise, but basically that doesn't matter. But it's just depends on the further calculations of the formula. So we didn't talk about an estimator for the covariance matrix. In this case, this is here an unbiased estimator for the covariance of X. And so we have a matrix in the data itself, but we are only considering here the covariance with respect to the different samples that we have, or elements of the samples. So here, if the samples are row-wise, we get this estimator for the covariance matrix. So we just take the transposed of the matrix here and multiply it by itself. And of course here I'm still in the range of the random variables with uppercase X. So, and if we now go to the data, we have a concrete realization, lowercase x in my notation, then we would have this matrix here, which has in the estimate, of course, that we then use has again this factor in front of it. But the main point is that this matrix that is appearing here is a symmetric positive semi-definite matrix, and it is even positive definite if we have more samples then entries in the sample. And if the data matrix has full rank, this means the data vectors are linear independent. So we don't have exactly the same elements in the sample. And again, the sample, an element in the sample is a vector itself. So this is a typical case, such that we have here a matrix and here a matrix, and we multiply this where the first one is transposed. Okay, and now this is a basic thing, and this is the interpretation in a stochastic way that we interpret this matrix as a realization of a random variable, and that we see it as or we know that it's an unbiased estimator for the covariance of the data. And this is something which we already had because eigenvalues were already a topic when we studied the optimality conditions, and so we have the definition of an eigenvalue, the definition of an eigenvector. We know how we can compute them. In the simple case, in the low dimension, we just use this determinant, but only for 2 or 3 dimensional matrices, so 2 by 2 or 3 by 3. In the general case, one would need a numerical algorithm to compute the eigenvalues. So it's not that easy to compute them, but at the moment here we just need the properties. So in general we are talking about complex matrices because the mathematical results are valid for complex matrices. Of course, we are mainly looking at real data, and the main thing then is, in general, a matrix has n complex eigenvalues. We have a real data matrix usually, but it may also have complex eigenvalues. And the matrix that we consider here is symmetric and positive semi-definite. And therefore we have additional properties, because symmetric matrix has only real eigenvalues, and this is the important thing. So again, going back, considering this matrix here, which together with this number here in front, with this fraction in front, would be an unbiased estimate for the covariance. But so the main thing is here we have a matrix which we want to analyze. The factor doesn't change the properties of the matrix because it's positive. And this matrix is symmetric. Thus, all eigenvalues are real, and we can also, what's called diagonalize the matrix. So there is an invertible matrix, a regular matrix, which can be combined here in this way with the diagonal matrix, where in the diagonal matrix there are the eigenvalues, and then we multiply with the inverse, and this gives the original matrix. So we can diagonalize it, so we can write it as a product of a matrix, a diagonal matrix, and the inverse of the first matrix. And in the matrix S, it can be easily seen here from the definition of eigenvalues and eigenvectors that the ith column of S is an eigenvector to the eigenvalue lambda I. So the Si, if we call it this way, are the eigenvectors. Moreover, these eigenvectors form an orthonormal basis, so they satisfy this relation here. If we take the scalar product between a pair of these eigenvectors, then we get 1 if the index is the same. If the index is not the same, we get a 0. So this is, they form an orthonormal basis. And as a consequence of that, they form a basis, every vector in Rn is a linear combination of the eigenvectors. So we can take any vector v, we find coefficients in R such that we can write the vector as a linear combination of the eigenvectors. If we consider this matrix here as a candidate, so this basically, and we can of course always add the fraction here 1 over m minus 1 here. So, but this matrix is a symmetric positive definite or positive semi-definite matrix. Then we even know that we only have positive or non-negative real eigenvalues. We already had this in the section or in the lecture about the optimality conditions. So we have an ordering of the eigenvalues, and here in this case I order them. The first one is the biggest one, and then we of course have also an ordering of the or we can identify with an eigenvalue the corresponding eigenvector, and these are called the principal components. So if I want to find the first principal component, then I'm meaning the eigenvector corresponding to the biggest eigenvalue. Okay, the theorem that we had has some consequences, and basically this was the last point in the theorem here, that every vector is a linear combination of the eigenvectors. The theorem that we just had has some useful consequence, and the first consequence is if I get a new data vector also in Rn, I can always represent it like this. So I always get coefficients Ci times the components, the principal components, and this linear combination builds up the new vector. And so if I can compute these coefficients, I can directly see which of these components are the most important in the new data vector that I have. And this I can use also to group data into different groups. If I have a data set, so I have already this matrix, I computed the principal components, and maybe I threw away some of the ones that have very small eigenvalues, so I just taken out the most important principal components, or the ones that I'm interested in. Then I can say, okay, I get a new data vector, and then I'm just looking for the coefficients of this principal components that I'm interested in, and then I can say, okay, this new vector has a very big component for, let's say, my first principal component Si, and this I can use to group the data into different groups according to which component is most dominant in the data vector. So I just say, I take the index here where the coefficient is the biggest one in magnitude, and then I say, okay, my new data vector goes in this one group. So this can also be used to cluster data, to identify data which are in some sense close to each other with respect to this principal components. I can also do the same looking at the deviation from the mean, of course, because if I apply my principal component analysis to the difference between my data set and the mean, which we did in the beginning, then it might make sense to not to look at the data itself, but also to look at the new data vector and its deviation from the ensemble mean. I can do the same thing. I get different coefficients here, but I can also do this. So I have several options. And the main question is now, of course, how can I find these components? But this is not very difficult, because if I apply the scalar product of this new data vector that I have with one of the principal components, or the eigenvectors, I can just insert this here. I know I have this representation, and then by just transposing this here means I just transpose the Si. I get here the scalar product of two of these eigenvectors, but they form an orthonormal basis. So all of the terms in the sum disappear. Just the Sk that I have here is remaining. So, and this, again, this scalar product here is 1. So I can easily compute the component in the representation, so the Ck, by just applying the scalar product of my new data vector times an Sk. And then I get the value of the kth coefficient, and I know which in this representation here, which parts are the most dominant by just looking at these coefficients. I can do the same thing if I consider the deviation from the mean. So then I take this here. Okay, so this was using the eigenvalue decomposition. We already had the singular value decomposition. As I said, when we were looking at the regression problem, so we found out that every matrix can be decomposed in this form, where we have two orthogonal matrices here, and then just a somehow diagonal matrix. And in the regression problem, we always had more equations, so m was bigger than n. Here in our application now, it can be both cases. We might have more members of the sample than the dimension of every member is, but it can also be the other way around. So we have these two cases. This was the case that we had in the regression. We had more data points than parameters in our model. So we have a rectangular matrix like this. Then we get here the U, and the sigma looks like this, has here a zero block under the diagonal. Here are the singular values. And here's the other orthogonal matrix. If we have now the problem that we have an underdetermined system, we could see it in the regression. But here we see it, we have less elements in the sample than every element has entries. So this would be my example in the beginning where m was 8. I had this 8 snapshots, but I had 100 points in every snapshot. Then I would have this rectangular matrix. Then this looks like this, and we have a zero block here. And the dimension of this sigma is only going to m. So if we now compute the singular value decomposition just of this data matrix, so not of the estimator for the covariance matrix, but just of the matrix B, x minus x bar, where this is the mean, we obtain this here with orthogonal matrix U and V and this diagonal style matrix. And if we then compute the estimator for the covariance matrix, or the matrix that we need inside, the estimator would have this additional factor in front. But if we compute then B transposed B, this is this matrix transposed times itself, then we can insert the singular value decomposition like this. We have to transpose this product here, and by the rules of transposition of matrices, the order changes then inside and everything is transposed. So we get a V there, we get a sigma transposed, and we get a U transposed. The U transposed meets here the other U, and this is an orthogonal matrix. So this gives the identity. This is a property that we have for orthogonal matrices, which is also very important when we solve the regression problem with the SVD. So this disappears, and we just end up with this here, and we have the two orthogonal matrices here outside, and then we have the product of these two diagonal matrices. And if we look at them, they look like this in the case m bigger than n, but then we can easily see that we just get a diagonal matrix with the squares of the singular values on the diagonal. If we do it in the other case where m is lower equal n, then we have the different different sizes here. So this gives now a longer number here, or a bigger number of rows, because this is sigma transposed. So we have now here an n and here an m. But again, this gives just multiplication of the diagonals, but we get additional zeros on the diagonal, because here these zero blocks meet each other. So we get this here, which is again an n times n matrix. But now m is smaller or equal to n, so we have eventually, if m is really smaller, we would have zeros here at the end. So now we can compare what we get with the eigenvalue decomposition and what we get with the singular value decomposition. So the singular value decomposition gives us that we directly decompose the matrix B, which is this difference here, and we can then obtain for B transpose B, V, the diagonal matrix here, and depending on the relation between M and N, there is here some zeros at the end, optionally, and then V transposed. So we have a representation of a matrix, a diagonal matrix, and another matrix. The eigenvalue decomposition directly gives us B transpose B, because we applied it on B transpose B. It gave us S D S minus 1. So the correspondence is that we can say we have S is equal to V, because these two things are the same. The D is just the diagonal of the singular values, where we set the singular values equal to 0 if I is bigger than M. So in this case here, this is the same matrix, just written in a more compact way. D is a diagonal matrix. And V transposed is S minus 1, because we know that the inverse of the orthogonal matrix is the transposed. So we have the same thing computed in two different ways, applying the singular value decomposition directly on the matrix B, or the eigenvalue decomposition on the transposed B transposed B. This is directly operating on the data matrix, and this, the eigenvalue decomposition, is operating on the covariance matrix if we we just don't have the factor here inside before the matrix. Okay, so and the main point also is that the singular values squared give the eigenvalues of B transposed B. The eigenvalues we saw in this matrix, because it's positive semi-definite, at least they are all non-negative. So this can be seen here also with a square. Yeah, okay, that's it basically. We saw principal component analysis, a tool for data analysis. We can base it on eigenvalue or singular value decomposition. They are both equivalent in some sense. And the data matrix that we treat can be interpreted as a covariance matrix, because we always had here that in this example, we used X minus X bar, and then the B transpose B is addition with a factor, then an estimator for the covariance. So this is an interpretation. And we can use the eigenvalues and singular values to detect the most important, that means the principal components of the data. And this can be used to reduce the data size by omitting components. This is the thing that we already had when treating the singular value decomposition in the first time in the lecture on regression. And we can also use it for data clustering. And that's it.